In stats, we started to wrap up t-tests. We had a handout that we started on Tuesday, I think it was. We finished off right there. In class, we may not have written that conclusion, but there it is. And you can see part B at the very bottom of the screen. Which error were we at risk of making? So this was measuring dissolved oxygen in a stream, possibly putting aquatic life at risk if DO was too low. We ended up failing to reject, so that means we are at risk of a type 2 error. If we are wrong, we are putting aquatic life at risk. All right, try not to say any more about water quality necessarily. I mean, if you know a lot about it, I guess you could elaborate, but I wouldn't risk being wrong in that regard because that's all they note up in the paragraph. So that's what we're worried about right there. On the back of this page, we look at paired data. You might hit pause and read through the paragraph and the example about caffeine dependence. So these are caffeine-dependent subjects, and they've been paired, which means, like another word for this was matched pair design, or in this case, test. It's a form of blocking. And they did this because I imagine they worry that, if one individual has stuff going on outside of in their normal life, where they could possibly be more depressed than another person, then the results of the caffeine test would be confounded. So they paired the subjects. In other words, they gave each subject, so write this down here, gave each subject both treatments. And this is really useful because each subject is their own control. If I compare one subject to another subject, they're not necessarily comparable because what if they have other life issues going on and that affects their depression score? So they're giving these subjects a caffeine pill, checking depression levels. They're giving them a placebo days later, hopefully checking depression scores. And not only just doing it that way, they're randomizing how they're giving the placebo and caffeine pill. So down here in part A, they ask you why they randomly give these. We'll answer that eventually. Down here on part B, they want us to carry out a test. That's what I'm really worried about. So we're going to dive into the test. And what you do when you have a paired test is for the state step, you need to define the difference you're measuring. So we are measuring the true mean difference in depression scores for caffeine, dependent subjects and it's important that you note how you were doing this. and they decided for us placebo minus caffeine. So I write that down somewhere on my paper. All right? Now we're going to assume that there's no difference between the two. So that's what our null is. We say the mean difference is 0. And we're going to test to see if there's an effect. If I'm doing placebo minus caffeine, I suspect that depression is going to be bigger, larger, than with caffeine. That means positive. So I suspect that these scores are going to be greater than 0. The differences are going to be greater than 0. I'm going to let alpha equal 0.5, and I'm going to grab my calculator. So we need to get the differences. That's all we care about. You can even make that note on your paper, maybe in the left margin. Once you have the differences, so that's going to go right there. The original lists are not needed. All right, so we need to, I know you could do this in your head, placebo minus caffeine, but if ever they give you a complicated number with decimals, it's nice to do this on the calculator. So grab your calculator, type those two lists into a spreadsheet. So I would call this one on the left something like caffeine or CAF, and the one on the right plaque or placebo, you can abbreviate. And I already did it right there. So maybe hit pause, rewind, type in those two lists, and get ready. So once you have that, you need to put your cursor right there where you see it blue. So that's the equals row, the formula row, and we're going placebo minus caffeine. So I'm just going to start typing plaque, and an equal sign is going to appear. So I type P, and look at that, there's a equal sign to the left of it, LAC minus CAF. And it's going to subtract all of them for us in a heartbeat. And there they are. I need to be able to pull this list, so I need to name this list. I'm going to name it C. And there they are. Rewind if you need to see that again. So now I have all my differences. You really don't have to write them down if you don't want to, but you can if you want. And we move to the plan step. So this was not a random sample, but treatments were randomly assigned, so that's worth noting. Random assignment of treatments. To 11 subjects. Now the bad thing is we only had 11, which is less than 30. But what you will typically see in a situation like this, when the sample size is too small, is you'll see a graph. So on your calculator, go to a home screen and click graph, and we want to graph C, the differences. Maybe I should have called it diff, but oh well. There's a dot plot. It's not really symmetric, but it's not like significantly skewed. If you're really nervous, change the plot type to normal probability plot, and it puts those on the bell curve, and those dots are all pretty close to the bell curve. because the black line is the bell curve. And so we can say it's approximately normal. So right here, even though the sample size is too small, we can say the graph is somewhat symmetric with no outliers. If you're nervous about being wrong on the outliers, you could look at a box plot. Sometimes they'll plot the box plot for you. You could refer to that normal probability plot that I just graphed and say the dots are all very close to the line of the bell curve. This is approximately normal. I almost forgot to say that. All right, let's move on to the math part. I'm going to run out of room. So we are doing a paired t-test. And we need to write down the mean difference, the standard deviation difference, the t-score, and the p-value. I didn't write the formula, so that is x bar d minus mu d over sd squared to n. So as I said before, you don't have to write the formula, you can just write the name of the test. So grab the calculator again. Let's run the test. We are doing a t-test. The calculator doesn't know the difference between paired and t-test, so they just have it typed as t-test. So t-test. I have data. It's all in list C. I'm assuming zero difference. The name of my data is C. I think it's positive, and I'm ready to go. There's T, there's the p-value, looks like it's significant. We're going to reject O, write down DF. Almost forgot that. There's our mean difference. And our standard deviation difference. We're ready to go. So x bar D is 7.3636. This was 6.9177. T was 3.5304 with 10 degrees of freedom. And we got 0027, which is small. And now we can conclude. And I don't think I have enough room. Let's see if I can fit it in that space. So I'm going to skip the word conclude and just write reject HO. Evidence suggests the true mean difference in depression score for these, I have to talk about that in a minute, caffeine dependent subjects is greater than 0. So what we could do in a follow-up sentence, that's like a generic conclusion. What we could say in a follow-up sentence right below that would be something along the lines of, I'm just out of room. There's nowhere to write this. Depression increases without caffeine. I mean, you could insert that into that conclusion that I wrote, but I don't know. I like to write it in 2 sentences. The last little thing on this was part A that I skipped. So let's go back to part A. And they ask you about the reason for random assignment. So let's make a note on the side of this about what random implies. If a sample is randomly taken, then we can generalize to a population. If we don't have a random sample, we can only talk about the people in that sample, like volunteers, this one. So that's why I had to be careful with my conclusion. I can't say this is the case for all caffeine-dependent people. If treatments are randomly assigned, then we can conclude whether there is an effect or not. So, on part A, why did they randomly assign the order? I mean, what I just wrote is the real reason, but they're asking you to explain why. Like, why was that important? And I would say something like, if subjects... Now, before I write this, you can think of just an example of how maybe depression could be a factor in regards to maybe taking the caffeine pill first for everyone versus taking the placebo pill first for everyone, or maybe a residual effect or whatever. If you can think of an example of bias when you don't randomly assign, then that is the sentence that you're aiming for. Have any kind of residual caffeine depression after taking a pill, it is important to randomize order to eliminate bias. All right. I hope that made sense. I'll see you later. Bye.